first going to consider a compressible system of R134A at a given temperature and pressure. And we were asked to find, in this case, the remaining thermodynamic property and indeed the quality, if we can speak about such a thing. We know that since we're given T and P, our governing equation is going to give us V when we're given T and P. Well, that would be called the equation of state. The equation of state is dependent upon the substance and the phase. In this case, we don't know the phase, so how are we going to find it? Let's draw the vapor pressure curve, P and T. The critical point, we know that above this curve it's liquid, below it's gas. So in this case, we have, oops, this should be a minus 12 degrees centigrade. And if we go look in our table for R134A at minus 12 degrees centigrade, we find that the pressure associated with that is 185.37 kPa. And my pressure is higher than that. It's at 320. So I'm going to be a liquid. My phase is a liquid phase. And the question becomes, what do we do when we have a liquid phase but we don't have tables, right? We don't have a tabular equation of state, a tabular EOS for liquid R134A. And there's no such thing as an ideal liquid law for us to be able to plug into. So what do? We have to make an assumption. And it's based upon the fact that the liquid phase doesn't really respond very strongly to pressure changes. It responds very strongly or stronger to temperature changes, but pressure changes, it's pretty much inert. So if I'm the Hulk and I'm pressing on this blob with all my might, I'm really not going to have the ability to change its volume. But if I heat it up a little bit or cool it down, I will be effective. We call this the incompressibility assumption. And I think the easiest way to understand why is that it's insensitive to pressure. We call it incompressibility, is it's insensitive. It doesn't want to change to pressure changes. Okay, so we use temperature changes. Right, we're going to focus on temperature, which is why in the saturation tables, a table giving temperatures comes before a table giving pressures, because the temperature data is usually more important, at least in terms of this assumption here. So we would assume that V is going to be equal to VF. Of course, this is the volume of liquid R134A. It's just the saturation point. That's okay, it's still liquid, and we have this at our given T. This is mathematically, so to speak, how we use this assumption, right? So this is the incompressibility assumption. In this case, VF is, in our problem at minus 12, 0.0007499 meters cubed per kilogram. And so this is our volume. It's an approximation because we're using an assumption, but it's a good one. And the last thing we're asked for is X. And X is really not applicable. That's because it's not mixed. Of course, we do know that X is the mass of the gas over the total mass. And so if you wanted to be picky, you could say, well, there's no gas in this, so X is 0. But we reserve this kind of nomenclature to talk about the special case that it's not just a liquid, but it's a liquid at the saturation point, right? So we don't want to say that X is equal to 0, even though mathematically, technically, it's the case. We want to reserve the nomenclature X equals 0 for a case where we're saturated but all liquid.